Hi everyone, NumPy is without a doubt the single most important library in Python when it comes to data science and machine learning. And in today's video, I will show you all essential functions with code examples that you should know. So if you follow this tutorial until the end, then you should have a solid foundation to tackle your data science tasks. Now, if this is too fast for you, then I have a full crash course on my channel that I will link here. This is a little bit slower and goes a little bit more in depth, so you can check this out. And additionally, I have a free NumPy ebook on my website, which is what you see here. This basically contains all the code examples from today's video, so you can keep this as a cheat sheet, and I will put the link in the description. And now, without further ado, let's get started. All right, so here I'm inside my IDE, and if you're wondering what you see here, so I'm using a 2Python notebook here, but I'm also using this inside of PyCharm. So this will give me a nice way of showing you the code and also the output. So the central part in NumPy is the multidimensional array, or ND array. So basically everything in NumPy revolves around mathematical operations with these arrays. And all operations are highly optimized so that it will be much faster than using normal pure Python code. So under the hood, a lot of the code is executed in C, which is one of the reasons why it's so fast. And now, of course, the first thing we want to do is we want to install NumPy, and we can do this with either pip install NumPy, or if you use Anaconda, then you can say conda install NumPy. And after that, you want to import NumPy as NP. So this is just the convention. I think everyone is importing it as NP. And then you can check the version like so. So let's actually run this. And then you see, in my case, it's successfully imported and we can see the version. So I think right now the latest version is 1.20 something. So in this case, it's 1.90.2. And now, as I said, the central object is the NumPy array. So we can create a NumPy array by giving it a Python list. And then we can inspect this array. So for example, we can print the shape, we can check the data type, the number of dimensions, the size, and also the item size. So let's run this. And then here we can see we have the array, the shape, the data type. The number of dimension is only 1 in this case, and later we will see a multidimensional array. And we have the size, so 5, and the item size is the size in bytes for each element. So this is 8 in this case for int64. And then we can do essential methods with an NumPy array. For example, we can access and change elements. This is the same like with a Python list. So we can access an element like this, and we can change an element like this. And we can also do element-wise math operations. So for example, we can do a matrix multiplication, or we can call different methods on a NumPy array. So we will get into this more later. For example, we can calculate the sum over all elements. So let's run this. And here we see we print the first element, then we change one element and print the new array. Then here we print the result after the matrix multiplication, and this is the sum over all elements. And by the way, this will be much faster than Python code, so we will also see this in a moment. Now here we see a quick comparison between an array and a list. So we basically create them the same way. So we create a list like so, and we create a NumPy array with this function, and then we can give it a list. So if we print this, they almost look the same, but they behave very differently. For example, if we do a multiplication with a list, so 2 times a list, then we will get the list repeated 2 times. So if we do L plus L, this would be the same. And on the other hand, if we do 2 times the NumPy array, then we get a multiplication for each element. So this is a big difference that you should know. And as a note here, basically we can say a function applied on a NumPy array operates element-wise. So let's run this. And here we see we have the list and the array, and they almost look the same. And now if we multiply the list, we get 2 times the list. And here we get each element multiplied by 2 for the array. So again, this is a big difference. Now let's have a look at how we do the dot product. So the dot product is very important in a lot of use cases. And if we want to do it in Python code, then we would have to do it like this. So the dot product is defined as the sum over the products of all the corresponding elements. So basically we need a for loop here and then multiply each corresponding element and sum it up. And in NumPy, this is much easier. So this is a one-liner. So we can say NumPy dot A and B. And also one nice thing to know, almost all functions are also instance methods, so we can use them directly on the array. So we can say a.b. And also in newer versions, we can use the @ sign for a dot product. So let's run this. And then we can see the result is the same for all operations. But now we will see that the NumPy code is much faster. So here I have a speed comparison of a NumPy array and a Python list. And we create a large list and also a large array. And by the way, we can convert a NumPy array back to a list like so. And then we calculate the dot product 1,000 times. And one time we do it with the Python way, and the second way we do it with the NumPy one-liner. And then we measure the time and run this. So let's do this and print this. And then here we see the time with lists, the time with array, and also the ratio. So it was almost 300 times faster. So this is a big difference that you should know. And I already mentioned this. One reason for this is that under the hood, C code is executed instead of Python code. And that's why it's so fast. Then let's have a look at how we create a multidimensional or ND array, or also known as a matrix. So we can create a ND array by passing in a list of lists like so. And if we print a and also a.shape, then we will see this is a 2 by 2 shape. So 2 rows and 2 columns. And again, we can access it like we do a one-dimensional array, so like so. But then we get only the first row. So if we want a particular element, then we have to give it 2 indices in this case. So the first one is for the row and the second one is for the column. Or we can do it comma separated. So we can say 0, 0. This will be the same as this. And we can also do slicing like we can do with a Python list. So this will give us all the rows in column 0, and this will give us all the columns in row 1. So let's run this. And here we have the 2D array and the shape, and then all the different elements that we access. Then we can, for example, calculate the transpose by calling a.t. So let's run this. And then here we see the transpose matrix of this. Then, as I said, we can do matrix multiplications. For example, we can do element-wise multiplications, or we can calculate the dot product with 2 arrays. And one important thing that we must remember is when we do this with a multidimensional array, then the inner dimensions must match. So the columns of the first, or the number of columns of the first matrix must be equal to the number of rows of the second matrix. So in this case, A is a 2 by 2 matrix. And if our B is, if we comment this out, if our B is a 2 by 3 matrix, then this will work. Because as I said, the number of columns in A is 2, and the number of rows in B is also 2. So if we say C equals A dot B and run this, then this will work. But now if we transpose this, so if we say B dot T, then this will be a 3 by 2 matrix, and now this does not work anymore. And then we will get this value error, the shapes are not aligned. So this is a very popular beginner mistake, that the shapes do not match and then it won't work. So keep that in mind. Then we can, for example, calculate the determinant with np.linalg.det. So this is for the linear algebra package. We also have the inverse in this package, so we can call the inverse like so. We can also call a diagonal matrix, and this has two different functionalities. So let's run this first and have a look at the example. So if we call this on a NumPy array, then we will get only the diagonal elements. So let's print A as well here. So let's run this. Then here we see we have A, and then we only get the diagonal elements 1 and 4. And if we call NumPy diag on these elements, so if we call this on a 1D vector, then we will get back a 2D, or not a 2D, so we will get a diagonal matrix with as many elements as we have here, and the rest filled with 0. Then let's have a look at how we do indexing, slicing, and Boolean indexing. So this is very similar to Python lists, so I will go over this very quickly. So we can access a array like so by giving it a comma separated value and index for each dimension. We can also do slicing with a colon, so this will go from start to end in this dimension. And for example, if you want the column 0, then we will go over all the rows and only take column 0. So let's run this. And then here we will see the different outputs for all the slicing operations. We can also do indexing starting from the end. So we can, for example, use -1 or -2. So if we access it like this, then we want to access the the last row and also the last column. So this is the last element. So let's run this. And then we will see we get the 12 from this matrix. So this is the last element in the last row and the last column. Then this is also very handy, and this is called Boolean indexing. So we have an array here, and then we get a array with the same shape with true or false based on the condition with this. So we can say Boolean index equals a greater 2. And if we run this, we get the same shape and false or true depending on this condition is met. And now we can use this array and put it back as an indexing operation into our A. And note that this will be a rank 1 array. So this will give back all the elements that are true. So in this case, it should be 3, 4, 5, and 6 as rank 1. So let's run this cell. And then we see we get the result. So this is working. So yeah, this is very handy. And instead of doing it like this, we can do it in only one concise statement. So we can access A where A is greater than 2. So if we run this, then we will get the same element. And then we have NumPy where. So this will give an array of the same size, and this will give us the option to modify the values. So we can say B equals NumPy where A is greater than 2. And if this is the case, then we will just use the value of A at this position. And otherwise we will put a -1. So if we run this, then we will see we get the same shape, and we will get -1s for all the positions where this is false. And then we have another way of doing indexing, and this is called fancy indexing. So with this, we can access multiple indices at once. For example, if we have one array like so, and then we can access it by giving it indices. So in this case, we want the element at index 1, 3, and 5. So it should be 19, 41, and 61. So let's run this. And then we get the result here. For example, let's say we want to have all the even elements of A. Then we could get the indices where A is even by saying even equals NumPy argware A modulo 2 equals 0, and then flatten this to get a 1D array like here. And then we can do this or use this as fancy indexing array and put it in our index. And now if we run this, then we will see here we have all the indices where A is even. And then if we put this back in A and access the elements, then we get only the even elements. Then let's have a look at how we do reshaping. For example, we have a 1D array by creating it like so. So we will see how we create arrays in a moment. We can do NumPy arrange and then from elements from 1 to 7. So this will look like this. And this is a 1D array. And then we can call a.reshape and, for example, specify the shape as tuple here, 2 by 3. This will give us an array with 2 rows and 3 columns. So let's run this. And then here we see the new array. But here we must be careful. So this will only work if the shapes can be used. So for example, if we use a 2 by 4 and run this, then we get an error, cannot reshape, because this is a incorrect shape here. So let's use this, or we can do the other way around. 3 by 2 is also possible. Then our array looks like this. Then another way of doing reshaping is using the new axis function. So this is used to create a new axis in the data. And this is, for example, needed when our model requires the data to be shaped in a certain manner. For example, let's print our A and A.shape. Then we will see it looks like this. And now if we apply A and then we access it like so and call NumPy new axis and then comma and then colon, this means it will just put all the rest here. And now if we print our new array and the new shape and run this, then we will see here we have a list of lists. And now we have the shape 1 by 6. And yeah, this is because a lot of time machine learning models expect it to be in this shape rather than in this shape. We could also do it the other way around. So we can say A and then colon first and then NumPy new axis. So let's run this as well. And then we see we have it the other way around. So we have 6 by 1. So basically we have a list and then one list, another list, another list, another list, and so on. Then let's have a look at how we do concatenation. So let's create 2 arrays and print them. So we can combine them into 1D by calling NumPy concatenate A and B and say the axis is none. So if we run this and have a look at our new array, then it looks like this. We can also add this as a new row by using axis equals 0. So if we run it like this, then we will see it put a new row here instead of putting it as 1D. And if we use axis equals 1 here, then we get a new column. So let's run this. And then we will see it concatenated it at the column dimension. Next to concatenate, we also have hstack and vstack. So hstack stacks the array in a sequence horizontally or column-wise. For example, here we have 2 arrays, and then we call NumPy hstack A and B and print this. And we do this with a second example. So let's run this. Then we see we have one column after the other. And the other way around is the vstack. So if we call np.vstack, and by the way, both hstack and vstack need a tuple, so be careful here. So if we do a vstack, then we get this row-wise appended. So here we have the new array where we have the first rows and then the second rows after each other. Then let's have a look at broadcasting. So broadcasting is also very important in NumPy. So let's say we have one array A and then one array B with only one row, and we want to apply these values to all the rows in A. So we would say A plus B. And in the beginning, I told you that all these operations are performed element-wise. So theoretically, we would need a value for each row as well. So we would have 1, 0, 1, and then comma 1, 0, 1, 1, 0, 1, 1, 0, 1. But this is actually very cumbersome. And this is where broadcasting comes into play. So NumPy can automatically determine this for us and is clever enough that we want to do this for each row. So this works. So now if we run this, then it will apply 1, 0, 1 to each row. So here in the first row, we have 1 plus 1 equals 2. 2 plus 0 equals still 0, and 3 plus 1 equals 4. And then we do this for the next row and the next row and the next row. So yeah, this is very handy. So here you don't have to specify these values for each row. You can only use this for one row, and then broadcasting does the rest for you. Then let's have a look at functions and axes. So we've already seen the concatenation function with different axes. And this is actually very important. So let's have a look at how this makes a difference. So here we have a 2D array A. And let's say we want to calculate a function. For example, we can use a.sum. And by default, the axis is none. And this means it will calculate the overall sum over all the elements in all rows. So if we do it like this, it will calculate the overall sum. If we say axis equals 0, then it will calculate it along the rows. So we will get one sum entry for each column. And if we say axis equals 1, then it will calculate it along the columns. So we will get one sum entry for each row. So let's run this. Then we see here we have the overall sum. Then with axis equals 0, we have one sum entry for each column. And here axis equals 1, we have one sum entry for each row. So yeah, be careful to always use the correct axis that you also want in your code. And yeah, we can also do this for all the other functions. For example, we have the statistical functions to get the mean. Then we have the std for the standard deviation, then var for the variance, and min and max. So all these functions work with the same principle with this axis argument. So let's run this, and then we also see the mean for all the different axes. Then let's have a look at data types. So if we specify an array and don't specify a data type, then NumPy will choose the data type for us. So if we run this, then it's probably an integer. And if we specify it as 1.0 or 2.0, then it's probably a float data type. So we will see this in a second. But we can also force a particular data type. And we can do this by saying, or by giving it the data type argument. And then we can use different data types, for example, NumPy int 64. This basically means how many bits we have. So 64 bits or 8 bytes in this example. And we also have int 32 and int 16, for example. So you will find all the data types on the documentation page. So yeah, let's run this. And yeah, here we see in the first example, we get an int. Then here we get a float, and here we forced it. So for us, we set int 64. For example, let's use int 32, and then we will see we get the new data type. And then let's have a look at copying. So here we want to be very careful, and this is the same with lists. So when we copy a list, then we also have to be careful. So let's say we have one array A, and we want to do a copy, and we do this by assigning it. So we say B equals A. then this will copy only the reference. And this means when we modify one element of B, then this will also modify this element in A. So now if we print A and B and run this, then we will see the first element here is 42 for A and for B. So be careful with this. So if you want to have an actual copy, you can say a.copy. So this is a function that you can use on a NumPy array. And now if we run this, then we will see that A is still the same. Then let's have a look at how we can generate arrays. So for example, we have NumPy zeros, and this needs a tuple, and here we can specify the size. So here we will get a 2 by 3 array filled with zeros. We have the same with NumPy ones. So here we have the same filled with ones. We can also get a specific value by calling NumPy full and then the size and then the value. Then we get the identity matrix by using NumPy I, and here we only need to give it one number for the dimensions. And for example, if we use 3, then we will get a 3 by 3 matrix. So let's run this, and here we see we have the identity matrix. Then we can use NumPy arrange. So if we run this, then we will get all the values from 0 up to this number, and this is excluded. Then we have NumPy linspace. So here we will give it a start and a stop value, and then the number of values we want. And then we will get 5 numbers in this case from 0 to 10, and it will determine the step widths for us. So in this case, the step size is 2.5 for each step. Then let's have a look at how we create random numbers. And for this, we have the numpy.random module. And here we can use different functions. For example, we can use random.random. This will give us a uniform distribution with values between 0 and 1. And this needs a tuple as the size. Then we have the random.randn function. This will give us a normal or Gaussian distribution. So this means the mean is 0 and it has unit variance. And here we need to be careful. So here we don't give it a tuple, but rather a comma-separated list of all the different sizes. So be careful here. So yeah, for example, if we run this, then we see we have the 2 different random arrays. So for example, if we create a very large array and then call the mean, the variance, and the standard deviation function on this and run this, then we see the mean is close to 0 and the variance is close to 1, and also the standard deviation is close to 1. So yeah, this works. Then we have random.randint, and this will give us a random integer between low and high with this size. So if we run this, then we will get a array of this size with values between 3 and 10. And 10 is excluded. And we don't need the first argument. If we do it like this, then it's starting at 0. So actually, if you run this again, then we will see we might get lower values here. We also have random choice. And here we also can give it a lower or only a upper bound. So in this case, 7. And then we will give it a size of 10. So this will give us 10 elements, and for each element it will do a random choice between 0 and 7. So if we run this, then we will see this is our resulting random choice. Oh, and sorry, here we don't give it a lower bound. So here we use only one integer, and this will automatically start at 0. So here we need only one argument, otherwise it doesn't work. And now if we want to give it multiple different values, we can also pass it a list here. So here it will draw random elements from this list. So let's run this. Then let's have a look at how we do linear algebra with NumPy. And for this, we have a dedicated module np.linalg. So in this, for example, we have the inverse and the determinant functions. And we also have the eig function, which will give us the eigenvalues and the eigenvectors, which is also very important a lot of times. So for example, if you have watched my machine learning from scratch tutorial about the PCA algorithm, there we used the eigen function. And one important thing to note here is that the eigenvectors are returned as column vectors. So let's run this. And then we can also solve linear systems with NumPy. So for example, if we have this linear system, so two equations and two unknowns, then the way to solve this would be to calculate, so we have this definition then, a times x equals b. And to get x, we have to calculate the inverse of a and then multiply it with b. So the inverse is very slow. So you could do it by saying np.linalg.inf and then .b, but this is actually not recommended. So there is a dedicated solve function for this. So we can call np.linalg.solve and then we pass it a and b. So if we run this, then we will get the same result, but this is usually much faster. So yeah, use this if you want to solve linear systems. And yeah, as last function, I want to show you how we can load data from CSV files. So for this, we have basically two different functions that we can use. So we can say numpy.loadtxt and then give it the CSV file, and we can specify different parameters. Or, which is even better, or maybe not better, but this is more flexible, we have numpy.gen from text. And yeah, so here you also give it the file name, and then you can use different parameters. And yeah, so I usually use this because this is a little bit more flexible, but I think usually both should be fine. So yeah, these are all the essential functions that you should know, and I hope you enjoyed this tutorial. And if you did so, then please hit the like button and consider subscribing to the channel. And then I hope to see you in the next video. Bye.